So let's look at the benzene mechanism then, electrophilic substitution. It doesn't have to actually be benzene, it could be a derivative of benzene like methyl benzene and so on. But if we combine it with nitro ions, then we're going to end up with with a nitrated form of whatever we started with, for example nitrobenzene. If we treat it with acylium ions, more detail needed there probably, then we end up acylating it, which is to add a carbonyl containing group to it. So things that we need to think about: how do we generate these ions, the mechanism itself, and what happens at the end. And I think it's important we look at balanced equations for the overall process for this one as well. So with no further ado, let's crack on. We'll start with the nitration one. Now, because this is revision, I don't want to use the easiest examples possible. That says nitration, believe it or not. So let's take something that isn't simply benzene. Let's have methyl benzene, okay? So that some points can be made. I'm not going to stick to a purely skeletal depiction, so I'm going to show my methyl group as a CH3. And imagine this. An exam question gives us that information that we've got methyl benzene, and they ask us to name and outline a mechanism. We're going to do a bit of talking about how do you make the nitro groups and so on as well, which leads to, say, this product. Okay? So if it was benzene, we could just stick the NO2 anywhere. But of course, this question's requiring us to put the NO2 on the carbon adjacent to the CH3. That's no big deal, but we just got to make sure we actually fulfill that part of the question, okay? So let's start with the generation of the electrophile. So here we've got the benzene ring acting as a nucleophile, an electron pair donor. In other words, the opening move of this mechanism will have an arrow coming from the benzene ring, more specifically from the delocalized electron system within the benzene's six-membered. Oh, what am I doing? Sorry, I'm drawing benzene. That's no good, is it? I don't need that just yet. So the reagents for the process that we're going to be calling nitration via the electrophilic substitution mechanism, we have to use concentrated nitric acid and concentrated sulfuric acid. And I think A-level chemistry teachers are suitably fixated on stressing that it's concentrated both, because if you say that one's conc and the other's not, you don't get the mark, or at least that's how it's been on past papers. So say conc this and conc that, and there you go. In other words, say concentrate twice. Reaction. I'm going to break this down into 2 steps, but then I'll give you the more commonly seen single step equation. It's an unusual example. We've got 2 strong acids doing acid-base reaction with each other. It's not redox, it's acid-base. What it is, the first hydrogen that sulfuric acid can give off is much more readily lost than any other that's in this equation here. And we get this unusual example of a strong acid, nitric acid, being forced into the role of being a base, like accepting a H+, to get H2NO3+. I'll draw the structure of that in a minute for your extra interest. And hydrogen sulfate is what's left after H2SO4's passed on one of its H's. That H2NO3+ species is inherently unstable, and it decomposes just spontaneously to our nitro ion that we're hoping for and water. So if we were to just write this as one equation, which is what I'd advise you to do, you've got your conc nitric acid and your concentrated sulfuric acids put together, and the sulfuric acid becomes hydrogen sulfate by giving off a H+, and giving the H+ to nitric acid ultimately leads to the formation of NO2+ and H2O. Now this isn't a reaction you'll have done in school, but it's like a one-pot synthesis, we call it. Like you literally put your chemical that you want to nitrate in the same vessel as your conc nitric and your conc sulfuric, and it's all there in one container reacting. So along with our methyl benzene and ultimately our products, there's also all of this stuff floating around. Okay, so just bear that in mind. Now, just take another quick look at this. We're aiming for methyl benzene to be nitrated once, so the NO2 group is adjacent to the methyl group, okay? If you're going to go ahead and do this for yourselves, now's the time to pause. So the mechanism itself is not that bad, it's pretty short, but people make mistakes on it. It's what we see when we have tests and so on, so we really can't afford to be throwing away marks at this point now. So the NO2+ ion is there present in the same pot as the methyl benzene because we've just made it in vitro, like in the vessel. The first mechanism step then is for this to bond with the N of the NO2 plus ion. It's absolutely essential that your arrow go into the N. Well, for a start, goes to the N of NO2 plus, but that arrow goes near the carbon that you plan to add the NO2 onto. And here, to meet the criteria of the question, it has to be a carbon adjacent to the methyl group, rather than like at the back over there, like 1,4, which isn't the right way around. So I've done that there. I've made sure my arrow goes near the carbon, which is like fitting the bill for the question, basically. We get an intermediate. This is where the horseshoe and the plus come in. So the methyl group is unaffected by all of this. To fulfill the requirement of the question, I'm putting the NO2 next to it. And at this point, I just expand out the H that was there all along, but it wasn't shown in the skeletal style that we've been using on the ring. There's a H there. Now, this horseshoe, I don't want to go on and on and on about stuff that we can get away with being less clear on, but also I want to help you. Every carbon in this ring is putting 1 electron into the delocalized system. So this circle represents 6 electrons delocalized around the benzene ring, conferring stability to it. This carbon that's had the NO2 added to it is now unable to contribute to that delocalized system because all of its electrons are tied up in bonding. A benzene ring is just like a little unit of graphite, basically. Every carbon's got 3 bonds and a spare electron. This doesn't have a spare electron anymore. So the delocalized system now only covers the other 5 carbons that can still contribute an electron. But the thing is, that delocalized system has just shed 2 electrons. So it was 6 for 6. Now you've got 5 carbons, but only 4 electrons delocalizing in there, because 2 of the 6 were used to make this NO2 plus bond. So it's not 6 for 6. Now it's like 5 carbons, 5 electrons that should be there, but there's only 4 in it. Or, alternatively, pretend I never said any of that, the horseshoe needs to visit the other 5 carbons, i.e. not the one that you've just added NO2 onto. And in the centre of that horseshoe, there must be a positive charge, because then you're getting the mark for the intermediate. Thirdly and finally, the CH bond breaks. So this is electrophilic substitution. The electrophile, the NO2 plus, is substituting out a H. So the CH bond breaks, so an arrow from the CH bond, and it has to go to your plus. Now, if you did the right mechanism, but ended up making, like 1,4, like methyl nitro isomer, you won't get the mark for the intermediate, but you should still get the marks for the arrows. I'll draw the product, even though it's a bit unnecessary, but there's a point to be made. So that's put 2 electrons and a carbon back into that delocalized system. So it's 6 for 6 again now. 6 carbons each putting an electron in, no charge, all the way around. And we've got our structure the way the question asked for it. And just to note, there's a H plus floating around as well that was kicked out. H left without taking an electron with it. Now, something actually does take that H plus, though we're not showing it here. We're just sort of, dropping it, like letting it break off. Something takes it. The hydrogen sulfate that was formed when H2SO4 and nitric acid, conc and conc, reacted, actually comes along and picks that off and makes itself back into H2SO4 unit. So at that point, H2SO4 was used up at the start along with nitric acid. The H2SO4 has been regenerated, so therefore it must be a catalyst. I'm just going to put cat regen there to make that point. So an overall balanced equation for this would have to be something like this. Methyl benzene and nitric acid, because that's definitely used up, the N is there now, were consumed in the presence of a concentrated sulfuric acid catalyst. The nitric acid was also concentrated. And we obviously get the organic product that we've shown the mechanism for the formation of. And then there's, let's have a look at this. There's a H2O. You might be thinking, where's the H2O come from? Go back. When we generated NO2 plus, we also generated a H2O. And that hasn't been used up since. That also balances now. There's a H there. There's another HNO3 there. NO2 gets put on, HH and the other O make the water. Really quickly, let's do the acylation mechanism, basically to the same effect. Now, you might have heard this referred to as Friedel-Crafts acylation. ultimately it's the other reaction that benzene does that we study, which isn't nitration. To acylate something is to add a carbonyl group onto something. Okay, that's an acyl group there. And the electrophile that we use is called an acylium ion. So I'll show an equation for the formation of one such thing. I'll start with ethanol chloride, and I'm going to react it with AlCl3. Now, just in case it helps, ethanol chloride there, obviously we've used that in the nucleophilic addition elimination mechanism. There it is. So you can see it's an acyl group with a Cl attached. AlCl3 is the thing to remember here. There's no catchy way of getting that, you've just got to know it. And it takes the Cl off ethanol chloride, it takes it off as a chloride ion. So AlCl3 gains a Cl minus, becomes a little covalent unit actually with a charge, AlCl4 minus, and then we're left with basically that. You see what I've done there? I've scribbled out the Cl and put a plus on the C. So we end up with CH3CO plus. Now, a quick aside on that, just because even though it's not relevant to the mechanism, it's the sort of thing like shapes of molecules, a bit of a curveball. I won't distract us for too long now. AlCl4 minus, well, we've met similar such chemicals in the transition metals topic. It's one of those weird examples of a covalent metal-non-metal thing, actually less rare than we think they are. Tetrahedral, 109.5 degrees, there's a few things we might say about its bonding and its shape. The acylium ion actually would be linear, because in the acid chloride it was trigonal planar, because you've got like a double bond, two single bonds. It's going to be roughly trig planar, you've got 3 bonds basically. This has only got 2 bonds, a double and a single, so I'd expect the bond angle to be 180 degrees. Completely irrelevant to the mechanism we're studying, but these little synoptic hide questions, you never know. Anyway, we've generated our acylium ion. I'm going to write that word out. Now, acylium is a general term for any carbonyl plus. That doesn't reflect that there are 2 carbons rather than any other number, but there it is, and that's our electrophile. We will just do it on benzene this time. So there's benzene. Along comes our acylium ion, and I'm clearly not drawing it linear, but it's okay, we get away with it for the sake of clarity. And as before, an arrow from the ring to the positively charged atom, which is the C+. Again, notice up there I just followed the convention of putting the charge in the top right corner, but strictly speaking it's on the carbon, which is part of the carbonyl, which is obviously that C there. That gives us the intermediate, very, very similar to what we had before. So there was a H on that carbon already. Now we've got the group that has just been attached. I've made a mistake. What is it? Well, I have drawn a ring that's supposed to be a horseshoe, so I'm immediately failing that. I did that really absent-mindedly. Okay, don't lose marks. So where the H and the carbonyl are attached, the horseshoe, remember, visits the other 5 carbons, and stick a plus in the middle of that ring. All of that for a mark, and now the final mark for the CH bond breaking and the electrons going into the ring, which again, you don't need the final product, but gives us the benzene ring's complete 6-membered delocalization system back, and the acyl group attached, and a H plus having been ejected. And as before, that H plus has to actually get taken by something, it doesn't just randomly drop off. What took it, though we're not showing it in the mechanism, was the AlCl4 minus, which was made during the generation of the electrophile. So there's a negative ion in the generation of both electrophiles. It's either hydrogen sulfate or this tetrachloroaluminate ion here, which take the H plus and regenerate the catalyst from it. It's the same in both cases. So the H plus here is the one that's lost there. You end up with AlCl3. That was there at the beginning, and now it's there at the end again in the same quantity, so it's been regenerated. And there must be another product, H and Cl. You get the corrosive, toxic gas, hydrogen chloride. Okay, this is not happening in aqueous conditions. If it did, the acyl chloride would react with water, because they do that. Remember, acyl chlorides and water, that's one of the reactions that go with nucleophilic addition elimination. So it wouldn't be like hydrochloric acid, it'd be hydrogen chloride, the gas. Balanced equation to finish this. The benzene ring is getting used up. The ethanol chloride that I used as the example is getting used up. The AlCl3 is a catalyst, so it shouldn't appear in the balanced equation as a reactant or a product. We get the acylated products, where that group has replaced the H, and that's because the H went out with the Cl from the acyl chloride. So there's my overall balanced equation for that. Everything's 1 to 1. Hope that's been helpful.